So now we just simplify here. What I'll do, I'll take this one on one side, that is x square minus y square. This one as it is here, y square x as it is, minus x square y. Now you can see here you have x minus y into x plus y. What is common from these two? X, y you will find common. So you are left with y from here, you are left with x from here. This is simple algebra, remember. Now further here, this will get cancelled, so you are left with minus sign there. So minus xy, cancelling y minus x from both the sides. And now here x equals to, take y common, so 1 plus x, and therefore y equals to x upon 1 plus x. So you have expressed y purely in form of x. This was implicit, now this is explicit. Now you just do dy by dx. So dy by dx equals to, division rule, 1 plus x the whole square, 1 plus x as it is here, differentiation of x1, minus here x as it is, differentiation of this bracket, which is here 0, here 1. So x will get cancelled, you can see. So you are here. So this will get cancelled, you are getting 1 upon 1 plus x square. But you are asked to prove minus this. So I think here there should be one extra minus sign. Here you must have minus, here you have minus, here you have minus, and therefore this is minus. So this is required dy by dx. Here it was little mistake. Anyway, so we have this. The important part is up to this, remember, or up to this, y equals to this expression. Question number 15, you are given this equals to c squared, and you want to show that 1 plus your dy by dx means y1 whole square upon y2. Here your numerator is 2, 3 by 2 equals to some constant. That's what you want to prove. Okay, so we just get y1, y2 and we place here. That's all in all about solution. Fine. So let's differentiate it with respect to x. Differentiating with respect to x, implicit function here. So twice chain rule. Imagine this is x minus a into differentiation of this is 1, this is 0. Imagine this is x twice y minus b into differentiation of this. Differentiation of y is y1, b is 0, equals to 0. I wrote y1 instead of dy by dx. You can divide by 2, so you are getting x minus a plus y minus b into y1 equals to 0. I want y1 first, so y1 equals to, take this one over there, so minus, I'll take this over there, minus x minus a upon y minus b. That's one thing. This is just by chain rule, remember. And then dividing by 2. This is dividing by 2 here, remember. Dividing by 2 at this place. We have this. And then make the y1 as a subject of the expression. This one over right hand side by this. Now again differentiation. Because you want y2. You want y2 here. So again differentiating. So differentiation of y1 with respect to x is y2. Minus sign as it is. Here I'll use the division rule. So x minus b the whole square. X minus b as it is here. Differentiation of x minus a 1 and 0, so this is 1, minus, now x minus a as it is, differentiation of y minus b, so y1 and 0, so here y1. I repeat this is simply by division rule, y minus b whole square, here y minus b. Y minus b as, let me rewrite this. So from this here, y2 equals to minus sign as it is, y minus b the whole square here, y minus b as it is, differentiation of x minus a, which is 1 and 0, minus, now x minus a as it is, differentiation of y minus b, which is y1 minus 0, so just y1. Okay, now we place the value of y1 from, let me call this as 1, because we want to simplify this. So therefore y2 equals to y minus b minus x minus a. What is y1? This value. So this will be plus, here this is whole square upon y minus b, the whole upon y minus b the whole square. Just putting y1 is with minus sign, so this become plus, x minus a is already there, and one more x minus a, so this become whole square upon y minus b. Take LCM here, so y2 equals to minus y minus b whole square plus x minus a the whole square upon y minus b and y minus b whole square, so y minus b the whole cube. 1 y minus b will come from this whole cube. You know that this is a known expression, which is c squared. You look at it given function, this is c squared. So therefore finally here you have minus c squared upon y minus b the whole cube. Call this as 2. From 1 and 2, now we put into that expression. So here you want this 1 plus y1 square the whole raised to 3 by 2 upon just y2. This is from 1 and 2. 1 plus y1 square is this x minus a the whole square upon y minus b the whole square. And what is y2 square? That is minus c square upon y minus b the whole cube. And here you have raised to 3 by 2, remember. This is from 1 and 2. So I'll write from 1 and 2. This is from 1 and 2. What I did, just placing the value of y1 and y2 over here. The whole square is already there. Now we just simplify this. So here y minus b the whole square plus x minus a the whole square, taking y minus b whole square as LCM. Now this square and this square root will get cancelled here. So this will come as here like this. If I write, this will come as y minus b the whole cube. This expression upon, see, if you take this outside, it's like this, y minus b the whole square raised to 3 by 2. So this 2 will get cancelled, so it will come as cube here. Upon this minus c square upon y minus b the whole cube. So this will get cancelled finally. You are left with therefore minus upon c square. And what is this? This is again c squared, you know, raised to 3 by 2. So again this will get cancelled. So you are just left with c cube upon c square. So this is just minus c. This is a constant independent of a and b, which is a constant independent of a and b, hence proved, right? So that's what you were asked to prove. So this is a good example. It's an important example. It's not difficult, remember. What you did in entire solution, you got y1, you got y2 here, and both the values you have placed in this expression and you have simplified and you got the constant finally. Next question, number 16. You have cos y equals to this expression. The question is, prove that the dy by dx equals to, this is what you want to prove, dy by dx equals to some expression here. Now this is again an equation about both the variables. But you can see that x can be expressed in form of y very easily. So cos y upon cosine of a plus y. Make the x as a subject of the expression. This is a good example again. So x equals to cos y upon this. Now you can see that this is an explicit function. X is purely expressed in y. So what I'll do, you have variable y on the right hand side. So I'll differentiate with respect to y, remember, not x, with respect to y. How do you write the derivative of x with respect to y? Dx by dy. And on the right hand side, you need to use the division rule. Square this function. Cos squared a plus y. There, cos a plus y as it is. What is derivative of cos y with respect to y? Minus sin y. You won't be having here dy by dx, remember, because this is in form of y. You are differentiating with respect to y. Minus, now which one as it is? Cos y as it is. Differentiation of this portion. So again you have chain rule. Imagine this as y. So differentiation of cos y is minus sin a plus y into differentiation of this portion. Being constant 0, derivative of y with respect to y is just 1. This is purely division rule in terms of y, remember. So differentiation is over now, just simplification. Denominator as it is. Here you have minus, this is plus. So let me rewrite here, cos a plus y into sin y. I'll keep minus sign here. Plus your cosine y into sin a plus y. Now if you observe numerator, it is that addition formula, sin x cos y minus cos x sin y. So it's addition formula of sin x plus y, a plus y minus y upon cos squared a plus y. What is numerator? Numerator, I'll repeat. It is which formula? It's like this, sin x cos y minus cos x sin y, remember. And you know that this is sin x minus y, addition formula, trig functions. Sin x cos y minus cos x sin y. Here x is a plus y. So a plus y minus y. Y will get cancelled. So we'll get the sin a upon cos squared a plus y. This is dy by dx by dy, remember. But you want dy by dx. So just you take the reciprocal. So cos squared a plus y upon sin a. This is your answer. So here we have parametric equations, in terms of t. So what we'll do, we get the dx by dt, dy by dt, and we take the ratio, and then we'll go for d square by dx square. So here differentiating with respect to t. So therefore dx by dt here, differentiation with respect to t. A constant as it is, differentiation of cos t is minus sin t. Product rule, t as it is, differentiation of sin t cos t plus Now differentiation of t is 1 and sin t as it is. So this sin t will goes away. You are getting at cos t. This is dx by dt. And now dy by dt. So differentiation of this portion with respect to t here. So therefore you have here again constant. So as it is, differentiation of sin t, it would be cos t minus product rule. Remember, t as it is, differentiation of cos t minus sin t. Actually here you have plus sign, but because of this minus, you have minus here. Now differentiation of t is 1 and cos t as it is. This is because of product rule. Cosine t will get cancelled. Here you are left with at sin t. This is dy by dt. And therefore dy by dx, that is just the ratio of these two, which is dy by dt upon dx by dt. So this is equals to here, what is dy by dt? At sin t. What is dx by dt? At cos t. So this will get cancelled. You are just left with tan t. This is dy by dx. Now we want d square y by dx square. You remember here, from dy by dx, you are finding d square y by dx square. So you are differentiating with respect to x, remember. You see what I had written here, differentiating with respect to t, here with respect to x. So you will get the d square y by dx square. That is equals to, you are differentiating with respect to x. You have variable t here, so you need to imagine there is x here. What's the derivative of 10x x square x? So sec square t into derivative by chain rule, derivative of t with respect to x, which is dt by dx. 90% students usually forget to write this step. This is very important step, remember. If it is here theta, then d theta by dx. So now you are through here. Just to put the value of dt by dx, that is from here, you call this as 1. This is dx by dt, remember. So take the reciprocal and put here. So sec square t into dt by dx is reciprocal of this. So that is 1 upon at cos t. So I'll write by 1 because of 1 here. And therefore finally this cos will be in the numerator, it will be sec cube upon at. This is d square y by dx square. This is your answer finally. Which is the most important step here? This one, remember. This is the most important step, into dt by dx. Why this? Because here your variable t, you are differentiating with respect to x. So you need to use the chain rule, and then again we place the value of dt by dx there. Question number 18, you want to show that here this function fx equals to modulus x the whole cube you are given, then f double dash exists. That means you can find double derivative for every x. Now you know that whenever you work with modulus, you have usually these three cases: positive, negative and 0. Case number 1, x greater than 0. You know modulus x become x. So therefore here fx equals to x cube. And therefore you can find f dash x, this is a standard polynomial function, 3x squared, f double dash x 6x. So here in this case you can say that f double dash x exists if x is greater than 0. Go for case number 2. That also you can do. X less than 0. It implies here modulus x, you know, minus x. So what will get here? If x equals to, what will get here? Fx equals to minus x cube. Therefore, what is f dash x? It is minus 3x square. What is f double dash x? You know it is minus 6x. This exists. Therefore, you can say that f double dash exists when if x less than 0. When this exists, if x less than 0. Case number 3 here, that is the most important case, which is if x is 0. X equals to 0 case. So first we'll show that f dash x exists, and then we'll show that f double dash exists. Now when you use the differentiability at 0, you need to use the definition. F dash 0, if you remember. Limit here, if you remember, x tends to 0, f of x minus f of 0 upon x minus 0. Which definition I've used? If you recall, f dash c, which is limit x tends to c, f of x minus f of c upon x minus c. In place of c, I place 0 here. I hope this is clear to you. Now we show that these exist. So this is limit x tends to 0. What is fx here? You know here fx will be modulus x the whole cube minus what is f of 0? You put 0 here, so this is 0 upon x. Now this might be positive or negative, so you can have this here, limit x tends to 0 plus or minus x cube upon x. So this is just x squared. So this is limit x tends to 0 plus or minus x squared, and as x tends to 0, this is 0. Remember. So what you have shown here, f dash at 0 exists and its value is 0. This is what you have shown here. F dash at 0 exists and its value is 0. Now we'll go for double derivative. Same procedure. So f double dash 0. How will write this? It's based on the previous only. Limit here x tends to 0 in form of previous derivative, that is f dash x minus f of f dash 0 upon x minus 0. What I did in this definition, I did double dash here. So double dash, so this becomes single dash, right? That much only. Okay, now you put the value limit x tends to 0. What is f dash x? First derivative is 3 times modulus x the whole square minus what is f dash 0? Just now you proved that this is 0 here. F dash 0 is 0 upon x. So this is equals to limit x tends to 0 here. This is plus or minus 3x squared upon x. So 1x will goes away. So you will get 0 here. What happened? 1x will get cancelled. If you want one more step, limit x tends to 0 plus or minus 3x. And then you just apply the limit. So this is 0 and therefore this is also 0. So in all the 3 cases, you have shown that, see case number 1, f double dash exists. Case number 2, f double dash exists. Case number 3, when it is 0, there also you have shown that f double dash exists. And therefore you can say that f double dash exists for all x. Exist for all x. That's solution. Next, you know, this is very standard result. Derivative of x raised to n is n into x raised to n minus 1, but we want to prove using PMI, remember. So if you remember PMI, principle of mathematical induction. Mathematical induction means PMI. So using here mathematical induction. Mathematical induction means using PMI from 11th standard. So there first first for n is equal to 1. First for n equals to 1, if you remember, we had two steps there. What is LHS? That is d by dx of x. And what's the derivative of x? That's 1. Go for RHS now, right hand side, RHS. Here 1 into x raised to 1 minus 1, that is 1 into x raised to 0, which is 1. So LHS equals to RHS. So P1 is true, if you remember. P1 is true. Just recall PMI from 11th standard. P1 is true. Now if you remember, for n is equal to k, we assume that the statement is true. For n is equal to k, assume that the statement is true. Assume that the statement is true. This is our assumption. Therefore, we have here d by dx of x raised to k equals to k into x raised to k minus 1. Call this as 1 where k belongs to n. This is assumption. For n is equal to k, statement is true. That means in the given statement, instead of n, you put k. We usually call this as 1. Now the last part in this one, that is we prove that the statement is true for statement is true for n is equal to k plus 1. For n is equal to k, this was assumption, remember. Now here we prove that the statement is true for k plus 1. Okay, so I'll start with LHS and I'll put n is equal to k plus 1. What is LHS? d by dx of x raised to k plus 1. What I did on LHS, on left hand side, in place of n, I have placed k plus 1, remember. We are going to prove this. You know PMI. Now this you can rewrite as x raised to k into x. That you know. Now you can use the product rule. So d by dx of x raised to k into this here differentiation of product rule. Differentiation of the first part x as it is. Plus now differentiation of x, that's a d by dx of x into x raised to k as it is. This is simply product rule. Now you know this portion from equation 1. You know answer to this from 1. So what is that? K into x raised to k minus 1. This is x as it is. This is 1 into x raised to k. This is by 1. What I did, instead of x raised to k, you have placed this value, remember, because of 1. This is 1, this is as it is. Now we just simplify. This is k into, here k minus 1 power, this is 1 power. So x raised to k plus x raised to k. Find x raised to k common. So k and 1 here, this is x raised to k. So this is RHS, right hand side. What you have proved? The statement is true. Statement is true for n is equal to k plus 1. See here, if I put here k plus 1, here also you are getting k plus 1, k plus 1. You see, that's what you are getting. Just put n equals to k plus 1. So here k plus 1 minus 1. So k. This is your RHS. So therefore, you can say that the P of k plus 1 is true, and therefore by PMI, if you remember, PMI means mathematical induction. By principle of mathematical induction, statement is true for statement is true for every n belongs to n. You know PMI is applicable only for natural numbers. Question number 20th, you are given this addition formula. We use the differentiation and we obtain the formula for cosine function. This is given to us, remember. So we just differentiate it. Differentiating, let's try it with respect to x here. Now you don't have x plus x here, so we imagine this is x. What's the derivative of sine x? Cos x. Cos a plus b into differentiation of this portion. So derivative of a with respect to x, dA by dx, plus differentiation of b with respect to x, dB by dx. This is because of chain rule. Imagine this bracket as x, derivative of sine x is cos x, into by chain rule differentiation of bracket. That is equals to, now on the right hand side, you have two terms. Here product, so use product rule. Here product, use the product rule. I'll keep sine a as it is. Differentiation of cos b, which is minus sine b into dB by dx by chain rule, remember. Differentiation of b with respect to x. Plus, now cosine b as it is into differentiation of sine a. What is that? Cosine a into dA by dx. Chain rule here. Plus, now we go to this term, cosine a as it is. Here cosine a as it is, differentiation of sine b, which is cos b into by chain rule dB by dx. Plus, now here sine b as it is. Sine b as it is, differentiation of cosine a, which is minus sine a into dA by dx. I've used simply product rule here. Sine a as it is, differentiation of cos b minus sine b, and so on. Now differentiation is over, we just simplify. So left hand side you keep as it is, cosine of a plus b into dA by dx plus dB by dx. That is equals to here. You see, you have dB by dx common, so I'll take dB by dx outside. What I'll get inside the bracket? I'll write this first. Cos a into cos b, then this minus sine a into sine b. Plus, now here I'll take dA by dx common. dA by dx I'll take common. So what I'll get inside the bracket? You see, cos a cos b minus sine a sine b. Now again on the RHS, so therefore let me write cosine a plus b into your dA by dx plus dB by dx, this is as it is. Here again the square bracket you take common, so inside the bracket cos a cos b minus sine a sine b. On RHS I'm taking this much common, so here you are left with dB by dx, here you are left with dA by dx. So now you can see this bracket will get cancelled, square bracket from both the sides. This will get cancelled from both the sides. Therefore, finally you are getting cos a plus b equals to cos a cos b minus sine a sine b. So this is your required addition formula proved for cosine function. Question number 21. Does there exist a function which is continuous everywhere but not differentiable at exactly 2 points? The answer is yes. Yes, you can find such functions. You just recall, I already discussed. You know that fx equals to modulus x. This is continuous everywhere. You know, we already proved this. Continuous everywhere. In the graph of modulus function, there is no break, you know. This is a continuous function, but not differentiable at 0. You know this much. Not differentiable at 0 only. Exactly 1 point it is not differentiable, remember. Same way here, if I take, for example, fx equals to x minus 1 with modulus. So again, this is continuous every way. Continuous every way. If you draw the rough graph of this, from 11th standard, it would look like this. So where it failed to be continuous at 1. So, but not differentiable at 1. You know this, you already proved this in one of the exercise question. Differentiable at 1. Now you add these two. So if I write fx equals to addition of these two, modulus x plus modulus x minus 1. This is continuous, this is continuous. You know that the sum of the two continuous functions is always continuous. So this is continuous every way. But not differentiable at 0 and 1. Same way it can be asked for 3 points also. If I take this function, for example, fx equals to modulus x plus modulus x minus 1 plus modulus x minus 2, then this is continuous everywhere, remember, continuous everywhere. You just, with the help of Google, you draw the graph of this. You will find many standard websites. There you can draw the graph of this. You will realize there will not be any break. But it is not differentiable at 3 points, 0, 1 and 2. Not differentiable at 0, 1 and 2. Can be asked for any number of points, remember. This should be clear to you. Question number 22. You are given this determinant and you want, this is not fx, this is y, I'm sorry. You want dy by dx. So what we'll do, I'll expand this determinant first. So fx into, inside the bracket, you know how to do this, m into c minus bn minus g of x into, inside the bracket, you know, l into c minus a into n plus hx into, inside the bracket, lb minus am. What we did, simply expansion of the determinant, you know this. Now we want dy by dx, so just get the dy by dx. dy by dx means differentiation of y with respect to x. So naturally this is a constant now. So the bracket as it is, with when you are constant with the function as it is, differentiation of fx, which is f dash x, plus, here minus, this is constant, so as it is, lc minus an as it is, constant with the function as it is, and differentiation of function, which is g dash x, plus this is constant, so as it is. Why it is a constant? Because there is no variable, and differentiation of h, which is h dash x. Now you just see, you could write this from determinant. Now this is just same as this, just f become f dash, g become g dash, and h become h dash. So I can rewrite in form of determinant like this. Just I'm doing reverse of the first step. So here f dash, here g dash, and here h dash. What about this one? L, M, N. What about this? Here A, B, C. You expand, you will get this step, and this is just RHS. That's what you wanted, so therefore proved. It's very simple. You expand first and then differentiate it, and then just you write in the form of determinant.